Now let's talk about ACI requirements, and this is from 2019. As always, phi Vn is greater than Vu. Remember, N means nominal in name only, and U is unusual, or maybe ultimate. We want the nominal strength, the reliable nominal strength, reduced by this phi factor, to be greater than the worst case load. What's new is that for shear, phi is 0.75, not 0.9 for flexure. Maybe another day we can talk about the historical evolution of this phi factor for shear. It used to be 0.85. And it's a very interesting discussion for another time. The shear strength components are a concrete strength and a steel strength. And we saw that Vs was AVFY, and the number of stirrups is approximately D divided by the spacing because of the 45-degree crack. And then this, what we're typically going to use for this class, is 2 squared F prime C BD, where again, let me mention in English units, that has to be in PSI. Here it is, the shear strength, AVFY D over S, and the number of stirrups is D divided by S. And each stirrup has a strength of AVFY. Okay, shear strength of the concrete has components of shear across this compression zone, VCZ. There's a dowel action, VD, and there's aggregate interlock, VA. And so it's very complicated. We can't ferret those out individually. And so we have this equation here that I just talked about in the previous video on VC. This is what we're going to have. And let me try to explain this. Okay, so if you had a set of blocks like this, can you see that if you pushed on these blocks tight enough, it can resist shear, right? If you push those blocks together tight enough and you lifted them up, they would have shear strength. Axial force increases shear strength. In our class, though, this is going to be 0 for beams, or not pre-stressed. There is axial force in columns. That's for another day. And so what we're going to have is 2 lambda F prime C BD versus 8 lambda rho to the 1/3. And remember, if rho is less than 1.56%, you're going to use this. And you can use that whenever you want. So in this class, we're going to use 2 lambda root F prime C. And this is for lightweight concrete. And no matter what, VC has to be less than 5 root F prime C. This is, however, if you have at least minimum stirrups. In the situation where you do not have stirrups, which again, I advise against, but if you're allowed to do it, so if you have less than the minimum, you don't get the 2 root F prime C, and the only difference is you have this lambda S factor. This is for size effect, and this is where these equations came from. They came out of concern for failure of large-scale beams in an airport hangar, paper put out by Danny Kuchma. And that led eventually to this change where we switched the equation over to what you see now. And this size effect factor, okay, is given here. And if you ever do decide to put no stirrups in a very big beam, which would be very, very unwise, this is what you would do. There are material requirements for this equation, these equations. Fy of your stirrups has to be less than or equal to 60 ksi, no high strength steel in the stirrups. And this root F prime C has to be less than 100, which means F prime C less than 10,000. Again, if you are not using minimum stirrups, which again is a bad idea. And if you have root minimum stirrups, you can let root F prime C be bigger than 100 psi. This is fancy concrete. This is over 10,000 psi concrete. So which equation are we going to use? Maybe we'll use this 2 root F prime C. And oh, this is an old slide, sorry. You can use the other equation, the one that's 8 root F prime C, 8 rho to the 1/3 root F prime C BD if rho is greater than 1.56%. Okay, for lightweight aggregate, you do reduce it with that lambda factor. If you happen to know FCT from a split cylinder test, you can replace square root F prime C with FCT over 6.7. Okay? That would be this. And that comes from this, which if you took 3210 from me last semester, we experimentally showed that this is conservative. This lambda factor though, the lambda square root F prime C, if it's all sand lightweight, lambda equals 0.75, and if it's sand lightweight, it's 0.85. All lightweight means all the aggregate has been replaced with lightweight aggregate and there's no sand. And sand lightweight means the aggregate, coarse aggregate has been replaced with lightweight aggregate, but you still have sand in the mixture. Okay, I think we'll stop there for now, and we'll continue this in the next video.